Hello everyone, on this video I'll be showing you what are the design equations to be used and what are the design steps to be used in order to design a microstrip patch antenna. Hope with this video you will be able to design antenna at different types of frequencies. Okay, let us start. These are all the different equations that we are going to use in order to design a antenna. Before designing any antenna, there are three steps to be considered. There are resonant frequency, material, relative permittivity of that material, and the thickness of that material. These three has to be chosen in before, because these plays a major role in the equations, because these has to be substituted in the equations that we are going to use in design. So step number one is to find the wavelength of a particular antenna, that is particular design, where lambda is c by f, where c is equals to velocity of a light, that is 3 into 10 power 8 meter per second, where in terms of mm it is 3 into 10 power 11, and f is the resonant frequency, the frequency that you have chosen to design the antenna. The step number two is width of the patch, where w is equals to c by 2f root 2 by epsilon r plus 1, where epsilon r is the relative permittivity of the material that you have chosen. The step number 3 is length of the patch, where L is equals to effective length minus 2 del L, where del L is extension length. Since we do not know these two, for these two alone we have separate formulas, where L effect is equals to C divided by 2f root epsilon REFF, where epsilon REFF stands for effective dielectric constant. So for this also we do not know, so for this alone we have another formula called this epsilon REFF, where epsilon R stands for same relative permittivity, where H stands for thickness of the material that you have chosen, and W stands for the width of the patch. And the next thing is del L, that is normalized extension in length. For this alone we have separate formula. If same alone we have found epsilon REFF, then W is width of the patch and H is the height of the that is thickness of the material. Okay, so we have found the length and width of the patch. Next thing is substrate length and width. In order to find the substrate length and width, these are the two equations that we are going to use, where Lg is substrate length or ground length, that is equals to L plus 6H, where L stands for length of the patch and plus 6H. H does not represent the thickness here. For H alone we have separate formula here. H is equals to 0.0606 lambda divided by epsilon. So we already have a formula for lambda, that is a step number one, so that you can be used here. And the next is feed length, that is transmission line, is equals to lambda g by 4, where lambda g stands for guided wavelength. So we do not know the guided wavelength, so for guided wavelength alone we have a separate formula called lambda g is equals to lambda divided by root epsilon REFF. So we already have found that epsilon REFF, so we need not to worry. So then this is a feed length, and for feed width alone you can take the half of the feed wave length. Next thing is, these are the equations for the radiation box. For axis position, length, width, height. For length alone it is lambda g by 6 plus lambda g by 6 plus Lg, where Lg is substrate length. And for width alone, instead of Lg will be replacing with Wg, that is width of the substrate, and height, instead of Lg and Wg you will be replacing with H, that is thickness of the material. And that's all. These are the standard equations that are being used in order to design a microstrip patch antenna. For any design you can use these design equations. So with an example, with a design example, I'll show you whether the antenna is resonating at a particular frequency or not. And nowadays the antennas that are being used practically should be of a miniature size. So I'll be designing an antenna at 15 gigahertz, so that we'll have a miniature size, that is 0.8 centimeter. Okay, I have already designed that antenna. I'll just show you the result. and the values that are obtained by equations. And the material that I have chosen is Artudurite 5880, to which the relative permittivity is 2.2. That 2.2 has to be substituted here, where C by 2F, that is C by 2 into 15 gigahertz, root 2 divided by 2.2 plus 1. So with that you will be able to find the width of the patch. So using that, I have found the width of the patch is 4.5 and the length of the patch is 6. So for different types of frequencies you can use these equations. Okay, next, substrate length and width. That using that equations I have found that substrate length is 8 and width is 9.5, that is 0.8 centimeter and 0.95 centimeter. So it is of a very miniature size. And then feed transmission line, the width length that I have found is 3.2, and the width you can choose as you like. You can analyze by giving different width, so that at what width you find better result that antenna can give, that width you can consider. Okay, that's all. And here in this design I have used inset feed, because when you use the inset feed there will be a proper impedance matching, so I have used inset feed. And these are the equations that you will be using for radiation box access position. Lambda g is guided wavelength that we have already found, lambda g here by 6 minus lambda g by 6 plus lambda by g 6. With that I have found access position as minus 1.7 comma minus 1.7 comma minus 1.7, and the length, the width and height 11.4, 12.9, 4.5. So with that, when you use these equations for radiation box, you will find that your antenna is placed exactly at the middle of the radiation box. See, you can be able to see that your antenna is exactly at the middle of the box. Okay, that's all. We'll run it and see whether the antenna is resonating exactly at 15 gigahertz with better return loss and good parameters. Okay, it's validated. We'll right click. Super. You can see here antenna is exactly resonating at 15 gigahertz. 15.06, 0.5 more or 0.5 less, it's not considered. Then we'll find the gain, create far field report, 3D polar plot, gain dB. Okay, fine. 3.5 is the gain of this antenna. Okay, that's all. Hope you liked the video, and you can use these design equations to design antennas at different types of frequencies. So higher the frequency, uh, lesser the size of the antenna will be there. That's all. You can see a flow table here. You can use these equations to design your antenna. Hope you like the video. Thank you.